Okay, today I'm going to show you a proof of the law of cosines, and then we will also solve a problem using this law. And if you listen to Khan's videos in Khan Academy, I want you to understand that I completely agree with what he says about the fact that memorizing this is something that you will tend to forget, but understanding it is something that can stay in your head, so you could derive it again if you ever needed to. So it's worth having on your list of references, and it's worth being familiar with, and for tests you might want to memorize it. But you can always rederive this formula. So I'm going to show you how. All right, so we are given a non-right triangle ABC. And let's assume that we know two sides and the angle between them. So we're going to say we know sides A and B, and that we know the measurement of angle C, right? So we know this angle and we know A and B. So how are we going to solve this problem? We can't use Pythagorean theorem because we don't know that it's right or it's not a right triangle. So what we're going to do is we're going to drop a vertical, kind of like we did in the law of sines, and we're going to make two triangles. All right. So first I want to look at, I would like to know this height right here, and I'd also like to find this side. And so I'm going to call this H, and just for fun we'll call this Z, just because I need a different variable. So I can use simple trigonometry to say that the sine of C is equal to opposite H over, oh, I probably shouldn't have called it H because of hypotenuse, but height, it's okay, B. And so H, if I solve for that, is equal to B sine C. And I can do the same thing with, I'll say cosine of C is equal to the Z value that I made over B. And so the Z side is equal to B cosine of C. So let me write these in. I'm just going to erase this H and this Z, and I'm going to actually write their values. I'm going to say this vertical is equal to B sine C, and this horizontal here is equal to B cosine C. So now if I want to know this length right here, I know that that length is equal to that total A minus B cosine of C. And now I can start to look at this other triangle I have over here, the one on the right-hand side of the vertical. And so I'm going to look at that and I'm going to say, or maybe I'll look at this entire triangle and I'll say, what do I know about this whole triangle? Well, I can say that, I'm going to move back to black. If I look at this triangle right here, I can say a squared plus b squared equals c squared, or in other words, not the same a, b, and c, but I can say those three sides squared equal each other. So I can say c squared is equal to that vertical one squared, so b sine of c squared plus a minus b cosine of c squared, right? So now I have to do a bunch of algebra. So I'm going to work this out. I'm going to say c squared is equal to b squared sine squared of c plus, and you have to use your FOIL thing, but this is a squared minus ab cosine of c plus b squared cosine squared of c. Does that look right to you? So let's rearrange terms a little bit. I'm going to say this is equal to b squared sine squared of c, and I'm going to move this one over and say plus b squared times cosine squared of c. Oops, I didn't have a parentheses. I didn't need that. Oops. Okay, and then I'm going to say plus a squared minus ab cosine of c. Now here's where this cool thing happens. I can take this b squared and I'm going to take it out of the first two terms and say that's times sine squared of c plus cosine squared of c. And that's still plus a squared minus ab cosine c. And so this is where you hopefully recognize this, but if you don't, I will show you why you should. This part right here, there's a Pythagorean identity that I can prove pretty easily that says that sine squared of theta plus cosine squared of theta equals 1. So we're going to substitute that in, and I'll prove that to you in a second, just in case you don't remember it. So that's equal to b squared times 1 plus a squared minus ab cosine c. So let's just rewrite this a little bit. I'm going to say c squared is equal to a squared plus b squared minus ab cosine of c. And that is your cosine law. Now, remember the Pythagorean theorem? It says that a squared plus b squared equals c squared. Or you could rewrite that to say c squared is equal to a squared plus b squared. So this is true for any right triangle, but you'll notice that it's kind of similar to this, which is true for any triangle. C squared is still equal to a squared plus b squared, but minus this little portion, the ab cosine c, if it is not a right triangle. And so that's a pretty nice relationship to have. So really quickly, I'm going to just scroll this up to the top, and I'm going to show you two things. First, I'll show you that Pythagorean identity. So let's do Pythagorean identity, in case you don't remember that. So here we go. Now this time we really do have a right triangle, and we're just going to do ABC. We're going to start with that a squared plus b squared equals c squared, right? But I want to use some cosines in here to figure out some stuff. And so let's say that I am going to divide, well, okay, first of all, we know that sine of c, the angle c, is equal to adjacent over hypotenuse, which, that we can't do that with the right angle. I'm sorry. I did that just totally wrong. Here. Let's see. What I really want to do is say, okay, can't find my pen. Sorry. Okay. I'm actually going to do this a different way first. Let's just divide everything by c squared in this equation. Okay. Trying to decide what order to do this proof in, because I haven't done it in a little while. So if we do this, we're going to get a over c squared plus b over c squared equals 1. You see that? It's just a rewriting of Pythagorean theorem. And then we can say, well, what is a over c? Well, if I'm looking at this angle theta, sine theta is equal to a over c. And again, if I'm looking at that one, I can say cosine of theta, so I was just picking the wrong angle before, sorry, of b over c. So I can replace these two right in that equation and say this is the same as sine theta squared plus cosine of theta squared equals 1. So that's the proof of the Pythagorean identity that I used right. If we scroll up, that's the thing I used right here to get to there. Okay, so that's your Pythagorean identity. This is also one of those things, memorize, use it. It will come up all the time. Simplify your life if you can apply that one. Okay, so lastly, we're just going to use this to solve a problem. So I am going to just say, what if I'm given any triangle? Let's say, I'm going to do this in blue so you can tell that this is just solving a problem, okay? I'm given some triangle ABC, and I know that this angle is 91 degrees, this side is 6, and this side is 13. So how can I solve this? Well, in this case, my enclosed angle is A, so really I should, I'm going to write my cosine law as if A is the main one. So I'm going to use this. C squared equals A squared plus B squared minus AB cosine C. So I'll write it that way. Equals A squared plus B squared minus AB cosine of C. But since I wrote this as a triangle ABC, it's easy for you to get confused and say, well, that's A and this is angle C. But it's not really, because what we're saying is, you could use any one of them that you want, but the one I want to use is the one I have the angle for, 91 degrees. So I'm really going to say that this side, I'm going to call this side C, even though it's whatever. And I'm going to say that that side, C squared, is equal to 6 squared plus 13 squared minus 6 times 13 times the cosine of 91 degrees. And then I just get out my trusty calculator, which I will do really quick while you all sit there and are bored in this video, because I should have done it before I started the video. And let's see, we will get 13 squared, and we go 6, enter 13 times. Okay, well, I'm getting a number that I don't believe. I just got 206. So I might have done the math wrong. Don't trust this number, but anyway, do it right in your calculator. And you, oh, I'm in radians. That's my problem. No, I was in degrees. I don't know. Anyway, it's possible that is the length, because 91 degrees is, no, I don't think that's right. Anyway, I could do the math, but I don't want to make you sit here while I do a super long video. And I will do a second recording for the next thing.